In genetics, there's this idea of the model organism, the fruit fly.
The Drosophila.
Right.
The little guy buzzing around your fruit bowl.
Exactly, but scientists love them. They breed fast, their genes are easy to track, and they basically help unlock the secrets of biology for everything else, humans included.
And the argument in the material we're looking at today is that AI has its own fruit fly.
Games.
Games. Chess, checkers, go.
And I think a lot of people hear AI learning to play games, and they just think, oh, that's cute. Engineers are making a better video game opponent.
Sure.
But this deep dive is about something much more fundamental. We are getting into adversarial search.
Which I have to say sounds a lot more intense than playing checkers.
It does, doesn't it?
Right.
But it really gets at what's going on. This isn't just you solving a crossword puzzle. This is about making a plan when someone else is actively planning against you.
That's the key. Think about your GPS. It's a search problem, for sure. It looks at traffic, distance. But the roads aren't trying to trick you. The highway doesn't, move an exit ramp just to mess with you.
Unless you hit construction, which, I don't know, sometimes feels personal.
Right. It really does. But even then, it's not actually out to get you. In adversarial search, you have another agent, an opponent, with a goal that is the exact opposite of yours. It's a zero-sum game.
Okay, let's define that. Zero-sum just means the total pie is fixed, right?
Exactly. If I win, you lose. A +1 for me is a -1 for you. It's the perfect little laboratory for studying decision-making because you have to assume the other person is playing perfectly.
Which is a terrifying thought. You can't just hope for a lucky break.
No luck. So to really understand how a machine thinks in this kind of environment, we have to visualize it. We have to see it as a tree.
A game tree.
A game tree. This is the foundation for everything. Imagine the current board state where all the pieces are is the root of the tree.
Yeah.
And every single legal move you can make is a branch shooting out from that root.
So in tic-tac-toe, I've got, maybe 9 branches at the start?
And from the end of each of your branches, new ones sprout for every single one of your opponent's possible replies. And so on and so on.
It must explode in size almost immediately.
Explodes is a gentle way to put it. For tic-tac-toe, yeah, it's small, you can map it out. But now let's talk about chess. The average number of moves on any given turn, the branching factor, is about 35.
So it gets 35 times bigger with every single turn.
Every turn. By the time you're a few moves in, the number of possible board states in that tree is something like 10 to the power of 40.
10 with 40 zeros. I saw that number in the research and just had to stop. That's more than the number of atoms in the known universe, isn't it?
It's a number so large, it's basically infinite. You can't build that tree. You can't store it. So
No.
the whole problem for game AI becomes, how do you make the perfect move when you can't possibly see the whole picture?
And that leads us to the granddaddy of all these algorithms, the one that tries to make sense of this impossible tree.
Minimax.
Minimax. It sounds like a supervillain.
It's pretty literal, actually. You have two players. We call the AI player Max.
Because it's trying to maximize its score.
And the opponent is MIN, because they're trying to minimize Max's score.
So minimax is basically just strategic paranoia.
That's a perfect way to put it. It is strategic paranoia. When the AI looks at a move, it doesn't ask what's the best possible outcome. It asks, if I make this move, what is the absolute worst thing my opponent can do to me?
It assumes the opponent is a genius who is out to get him.
A perfect malicious genius. The algorithm goes all the way down the tree to the end, states win, lose, or draw, assigns a score, and then backs that score up the tree layer by layer.
So it says, okay, if I go this way, MIN can force a checkmate. But if I go that way, the worst MIN can do is force a draw.
So I'll take the draw. I minimize the maximum damage you can inflict, hence minimax.
But wait, we just said the tree is effectively infinite. Minimax needs to see the end of the game to work, doesn't it?
It does, and in its pure form, you just can't use it for chess. I mean, the universe would end before it made its first move. So researchers had to get clever. They needed a way to ignore huge chunks of the tree.
This is pruning, right? Like gardening for algorithms. You're just chopping off branches you don't need.
Exactly. It's called alpha-beta pruning, and it's a massive, massive efficiency gain.
And the logic here is actually super intuitive. It's something we all do.
Oh, totally. Imagine you're picking a restaurant. You look at one place, the menu looks great, but then you see the health score is a D.
Okay, hard pass.
Right. You still need to check if they have a good wine list?
No, I'm out. The D rating was the deal breaker.
You've just pruned that entire decision branch. Alpha beta does the same thing. The computer starts analyzing one of its moves, it looks down that path and finds a response from the opponent that is just catastrophic.
Like, oh, if I move my knight here, they can just take my queen for free.
Exactly. The moment it sees that one single devastating reply, it stops. It completely stops analyzing that initial move. It doesn't matter if there are a million other wonderful possibilities down that path. The fact that MIN can destroy you makes the whole branch worthless.
You prune it. And the text says this basically doubles the search depth.
At least. It's the difference between seeing 2 moves ahead and seeing 10. But even with pruning, you can't see to the end of a chess game. You just run out of time.
You get a wall.
You hit a wall and you have to stop and, well, you have to guess. It's called a heuristic evaluation function.
Guess sounds a bit loose for AI.
It's an educated guess. The computer looks at the board where it stopped and just scores it based on a checklist. How many pieces do I have? Pawn is 1 point, queen is 9.
That classic point system.
Right, plus other things. Is my king safe? Do I control the center? It adds it all up and gets a score. +2 means I'm probably winning.
But because it is just a snapshot, an estimate, it can lead to some really weird AI behavior. The notes mention something called the horizon effect.
Oh, the horizon effect is fantastic. It's so deeply human, it's basically procrastination as an algorithm.
Okay, walk me through that. How does a supercomputer procrastinate?
So imagine the computer can search, say, 8 moves ahead. That's its horizon. It looks down one path and sees that on move 6, it's going to lose its queen, an unavoidable disaster. So it panics, it looks for any other option, and it finds one. It can sacrifice a pawn to put the opponent in check. A pointless but annoying move.
Okay.
The opponent has to respond to the check. That wastes the move. So now the queen isn't captured until move 9.
Which is beyond the horizon.
It's past the edge of the world for the AI. It can't see it anymore, so the computer thinks, phew, I saved my queen. It makes the useless pawn sacrifice, feels great. And then a few moves later, the horizon shifts forward, and oh look, the queen gets captured anyway.
It just pushed the inevitable disaster off a cliff where it couldn't see it.
And it lost a pawn for the trouble, just to delay the bad news.
I feel like I do that with my taxes.
We all do. The solution, by the way, is something called quiescent search.
Which means?
It just means don't stop thinking when everything is on fire. If you reach your search limit, but the board is in the middle of a flurry of captures, a noisy state, the AI is forced to search a little deeper until things calm down.
Until the board is quiescent.
Exactly. Wait for the chaos to settle before you make your final judgment.
That's some solid life advice right there. So we've got this whole complex system of searching, pruning, and evaluating. But sometimes the smartest move is not to think at all.
It's to just look it up. The lookup table. Humans do this. Grandmasters aren't calculating the first 10 moves of a game. They're playing from memory. It's book.
And computers have taken this to an insane extreme, especially in the end game. And with checkers, specifically.
Chinook. Yeah, this is a huge moment in AI history.
Jonathan Schaefer's program.
His team decided to just solve checkers. Not just play it well, but solve it. And they did it by working backward, retrograde analysis.
So they started from checkmate and worked their way to the beginning.
Sort of. They generated every possible endgame position with 10 or fewer pieces on the board.
And how many positions is that?
It's a database with 39 trillion entries.
39 trillion.
For every single one of those positions, they know with absolute mathematical certainty whether it's a win, a loss, or a draw.
So if I'm playing against Chinook and we trade pieces until there are only 10 left.
It's over. The thinking part is done. You might play for another 20 moves, but Chinook is just looking up the answers in its giant answer key.
And what was the result?
They proved that if both players play perfectly, checkers is a draw. Every time. The game is solved.
So the only winning move is not to play.
Or to just accept the draw from the start. Now, chess is not solved, but we have to talk about the big one. Deep Blue.
IBM versus Kasparov, 1997. The moment AI really hit the mainstream.
It was, but the reading here makes a really important point. People think of Deep Blue as this brilliant thinking machine.
It wasn't.
It was a monster, but it was a brute. It was all custom hardware. Specialized chips designed to do nothing but play chess. It could analyze 30 billion positions per move.
30 billion?
Kasparov wasn't outthought, he was outcalculated. The machine could just see further down the tree than any human ever could. It shattered the idea that human intuition was some kind of magic that brute force couldn't touch.
But here's the thing with chess and checkers. They're perfect information games. I see all your pieces, you see all of mine. There's no luck.
Right. It's deterministic.
But most of life isn't like that. There's luck. There are dice rolls. How does AI handle a game like backgammon?
Okay, so this is the next level. Stochastic games. And the game tree gets more complicated. It's not just Max's turn, then MIN's turn. Now you have chance nodes.
A dice roll.
A dice roll.
Sure.
A fork in the road where probability takes over. You can make your move, but then you have to account for all possible dice rolls that could happen next.
So minimax breaks down here, doesn't it? You can't just assume the worst-case scenario from the dice.
Exactly. You have to use something called expectiminimax.
That's a mouthful.
It is. But all it means is that instead of picking the best or worst path, you calculate the weighted average of all the possible random outcomes.
The expected value.
The expected value. And this changes things in a subtle but crucial way. In chess, a win is a win. The score doesn't really matter. A checkmate in 2 moves is just as good as a checkmate in 10.
You don't get style points.
Right. But in backgammon, the magnitude matters. A move that gives you a 90% chance to win $10 is very different from a move that gives you a 10% chance to win $1,000.
The math is totally different. The AI has to understand risk.
It has to weigh probability against payoff. This is what the program TD Gammon did so well. It used a neural network, played millions of games against itself, and got so good it actually taught human experts new opening moves.
The student becomes the master. Okay, but we're still not all the way there. In backgammon, I can still see all the pieces. What happens when you add the fog of war?
Partial observability. This is where it gets really messy and really close to the real world. Think about poker, or the game they use as an example, Kriegspiel.
Invisible chess.
Invisible chess, you have your board, I have mine, and we can't see each other's pieces. A referee just tells us if a move is legal or if we got to check.
That sounds impossible. How can you plan if you don't even know where the enemy is?
You can't track one board state, you have to track a belief state.
Which is what?
It's the set of all possible boards that could exist, given what you know.
So it's like Schrodinger's chess. The opponent's queen is in every possible legal square at once until you try to move there and find out.
That's a great way to put it. And your goal is to find a move that's good, or at least not terrible, across most of those possibilities.
Now, there's a strategy for card games, like bridge, that was mentioned, averaging over clairvoyance.
It's a clever hack.
Yeah.
The AI doesn't know what cards you're holding, so it just says, fine, I'll deal out a random hand for you in my head. Now it's a perfect information game.
It solves that imaginary game.
Then it throws those cards away, deals another random hand, solves that one. It does this hundreds of times and averages out which move was best most often.
But the text points out this has a huge fatal flaw. The road A versus road B problem.
Oh, this is a classic. It shows the blind spot perfectly.
Okay, so picture this. You're at a crossroads. Road A leads to a guaranteed, pretty good prize.
Okay, safe bet.
Road B leads to a fork. At that fork, there's a sign that points one way to a massive, amazing prize and the other way to a deadly cliff.
Right.
But you can't see the sign from where you're standing now.
Right. So as a human, what do?
You take road A. Road B is way too risky.
Of course. But the AI using this clairvoyance method gets it wrong. In its simulations, it pretends it can see the sign.
So in one simulation, it sees the sign says, go left to the prize, and it thinks, great, road B is the winner.
Then it runs another simulation where the sign says, go right. It thinks, okay, in that world, I also take road B and just follow the sign.
Because it assumes it will have perfect information when it gets there, it concludes that road B is always the better choice. So in the real world, it confidently takes road B.
And walks right off the cliff. It completely fails to understand the value of uncertainty and the need to make moves that gather information.
Which brings us to the final boss. The game that stumped AI for decades after chess fell. Go.
The ancient game on that giant 19 by 19 grid.
Why was Go so much harder?
The branching factor. Remember, chess was around 35, Go is 361. The tree is just, it's too vast. You can't brute force it. Minimax and pruning just don't get you anywhere.
So the Deep Blue approach was a total failure.
Completely. For years, the best Go programs couldn't beat a decent amateur. To solve Go, AI had to basically throw out the old playbook and embrace randomness. Monte Carlo simulations.
The rollout method.
Exactly. The computer looks at a potential move, but instead of trying to calculate the perfect series of replies, it just plays the rest of the game out thousands of times against itself, with both sides making completely random moves.
It just flails around until the game's over.
Thousands of times a second. Just random flailing. And then it looks at the results and says, huh, When I started with this move, I won 62% of the random games.
That feels so unintelligent. It's like throwing spaghetti at a wall.
It starts that way, but it gets smarter. It starts to notice which random moves tend to lead to wins, and it biases the future simulations to explore those paths more. It's like a spotlight that starts out wide and slowly narrows in on the best options.
So it focuses the spaghetti throwing.
It focuses the spaghetti throwing, and that's what powered AlphaGo. It was this huge leap that showed you don't always need perfect, crisp logic. Sometimes you can solve a problem by just simulating enough possible futures.
It's a huge shift in thinking. We went from the rigid paranoid logic of minimax in chess to managing probability in backgammon, to navigating the fog of war in Kriegspiel, and finally to these massive statistical simulations in Go.
It's a story about AI learning to deal with uncertainty. Early game AI needed everything to be known. It needed a perfect map. Modern AI is getting comfortable with the fog.
And that really seems to be the big takeaway here. This whole journey isn't just about faster processors. It's about finding smarter ways to deal with that horizon, the point beyond which you just can't see.
Exactly. It's all about making the best decision you can with the incomplete information you have.
Which leads to this final, pretty provocative thought from the source material. It says that game theory can view any multi-agent system as a game.
Economics, international relations, corporate negotiations, they're all games in that mathematical sense.
So if we have AI that can solve a game like checkers by working backward from the end of time, and an AI that can master Go by playing out thousands of random futures, how far are we from applying that kind of adversarial search to, say, a real-world peace negotiation?
It's a huge question. If you're at the table and the other side is being advised by an algorithm that has already simulated the next 10,000 permutations of your conversation.
Are you even negotiating anymore? Or are you just playing a game you've already lost?
Or maybe you're just a node on their search tree, one that's about to be pruned.
On that slightly chilling thought, we'll leave you to think about your next move. Thanks for joining us for the deep dive.
Keep thinking.